In the last module, we have discussed Wilcoxon sign rank test and established some properties. In the current module, we start with establishing a relation between Wilcoxon sign rank test and the sum of positive Walsh averages. This representation will be used to establish unbiasedness and consistency of Wilcoxon sign rank test. Later on, we shall find the large sample distribution of Wilcoxon sign rank test and hence give a large sample test. As an application, we shall discuss how Wilcoxon sign rank test can be used to infer symmetry of the underlying distributions. Lastly, we shall discuss the determination of sample size subject to some constraints on size and power of the Wilcoxon sign rank test. We have thus defined Wilcoxon sign rank statistic. We have discussed the nature and definition of such a statistic and their use in testing problems. We have also calculated some summary measures like expected value and variance of such a statistic under the null hypothesis. And finally, we have discussed how to calculate the distribution of T under H0 for small values of n. Now, we shall discuss some other type of properties, that is consistency and unbiasedness, confidence interval, etc. Now, we start with the representation of such a statistic in terms of Walsh averages. Define a Walsh average as the arithmetic mean of xi and xj for 1 less than equal to I less than equal to j less than equal to small n. That is wij equal to xi plus xj by 2. Then T can be expressed as the number of positive Walsh averages. That is T equal to summation j from 1 to n summation I from 1 to j indicator xi plus xj by 2 greater than 0. We shall give just an outline of the above representation. Observe that for j greater than I, x ordered I less than x ordered j, and hence x ordered j greater than 0 is sufficient to ensure x ordered I plus x ordered j is positive. Hence, indicator x ordered I plus x ordered j greater than 0 equal to 1 if x ordered j greater than 0. Now, if x ordered I less than 0, then x ordered I plus x ordered j is positive, which implies modulus of x ordered I less than x ordered j provided x ordered j is positive. Thus, indicator x ordered I plus x ordered j greater than 0 equal to 1 if and only if modulus of x ordered I less than x ordered j and x ordered j greater than 0. Now, for I equal to j, indicator x ordered I plus x ordered j greater than 0 is nothing but indicator x ordered j greater than 0, and hence indicator x ordered j greater than 0 equal to 1 if x ordered j is positive. Hence, for x ordered j greater than 0 in summation I from 1 to j indicator x ordered I plus x ordered j greater than 0, only those I will contribute for which modulus of x ordered I less than x ordered j. Thus, summation I from 1 to j indicator x ordered I plus x ordered j greater than 0 is nothing but the sign rank of x ordered j for positive x ordered j. Then, with the already introduced notation rj plus is summation j from 1 to I indicator x ordered I plus x ordered j greater than 0 provided x ordered j greater than 0. Equivalently, we can write the above as indicator x ordered j greater than 0 multiplied by rj plus equal to summation I from 1 to j indicator x ordered I plus x ordered j greater than 0. Summing the both sides over j from 1 to small n, the desired expression follows as summation j from 1 to n indicator x ordered j greater than 0 multiplied by rj plus is nothing but summation j running from 1 to small n zj multiplied by rj plus. Next, we shall consider the representation of T in terms of U statistic. Actually, T is not a U statistic, but it can be expressed as a weighted sum of two U statistics. Consider the already discussed representation in terms of Walsh averages. That is, T is the number of pairs xi xj such that xi plus xj by 2 is positive where I less than equal to j. Now, separating I equal to j and I less than j, we get T as the number of xi such that xi greater than 0 plus number of xi xj such that xi plus xj greater than 0 for I less than j. Now, the first one is nothing but n choose 1 multiplied by u1, and the second quantity is nothing but n choose 2 multiplied by u2, where u1 is a U statistic with kernel indicator x1 greater than 0 and u2 is a U statistic with kernel indicator x1 plus x2 greater than 0. Thus, T can be expressed as a weighted sum of two U statistics, one with kernel unity and the other with kernel 2. Now, we talk about a large sample property of the Wilcoxon sign rank test, namely consistency. Specifically, we consider testing theta equal to 0 against theta greater than 0. Now, signed rank test can be equivalently expressed in terms of T divided by n into n plus 1 by 2. From the convergence of U statistic, we find that for any theta, U1 converges in probability to probability x1 greater than 0 and U2 converges in probability to probability x1 plus x2 greater than 0. Again, n choose 1 divided by n into n plus 1 by 2 tends to 0 and n choose 2 divided by n into n plus 1 by 2 tends to 1 as n tends to infinity. Thus, combining all these, we find that for any theta, T by n into n plus 1 by 2 converges in probability to probability x1 plus x2 greater than 0. Now, define mu f equal to probability x1 plus x2 greater than 0. Then, under theta equal to 0, mu f is nothing but expected value of the indicator x1 plus x2 greater than 0, which can be expressed as double expected value of indicator x1 plus x2 greater than 0 given x2. Now, the conditional expectation, that is expected value of x1 plus x2 greater than 0 given x2, is nothing but the probability x1 greater than minus x2 given x2, that is 1 minus f of minus x2. Thus, mu f is the expected value of 1 minus capital F of minus x2. Now, due to symmetry, 1 minus capital F of minus x2 is nothing but f of x2. Since fx2 has a rectangular distribution over 0, 1, we get expected value of fx2 as half. Thus, we get under theta equal to 0, mu f as half. Since for any I, xi has a distribution fx minus theta implies and implied by xi minus theta has a distribution fx, the event x1 plus x2 greater than 0 under theta equal to 0 is a subset of that under theta greater than 0, and hence probability x1 plus x2 greater than 0 under theta exceeds half whenever theta is greater than 0. Thus, mu f equal to half when theta equal to 0 and mu f greater than half when theta greater than 0, and hence sign rank test is consistent against the alternative theta greater than 0. Consistency against the alternative theta less than 0 can also be proved. However, for theta not equal to 0, we use the statistic modulus of t by n into n plus 1 by 2 minus half and proceed as before to prove the consistency. Thus, consistency of sign rank test is established. Now, we shall show that sign rank test is unbiased. Consider testing theta equal to 0 against the alternative theta greater than 0 and the representation t theta equal to number of xi xj such that xi plus xj by 2 greater than theta for I less than equal to j. Then T naught is our test statistic, and the power function can be expressed as probability T naught greater than T alpha under theta plus probability of T naught equal to T alpha evaluated under theta multiplied by A. Since probability of the event T naught equal to T alpha under theta is nothing but the difference probability T naught greater than T alpha minus probability T naught greater than T alpha minus 1, both evaluated under theta, power function can also be expressed as A multiplied by probability T naught greater than T alpha minus 1 plus 1 minus A probability T naught greater than T alpha, where both the probabilities are evaluated under theta. Since for each I, xi has a distribution fx minus theta is equivalent to xi minus theta has a distribution fx, T naught is expected to be larger under theta than under theta equal to 0. Thus, T naught under theta is stochastically larger than T naught under theta equal to 0. Thus, under any theta greater than 0, probability of the event T naught greater than k under theta is greater than probability of the event T naught greater than k evaluated under theta equal to 0. Hence, the power function exceeds A into probability of T naught greater than T alpha minus 1 plus 1 minus A into probability T naught greater than T alpha, where both the probabilities are evaluated under theta equal to 0. Since the tests are of size alpha, the power function exceeds alpha, and hence we get that the right-tailed size alpha Wilcoxon sign rank test is unbiased. Similarly, unbiasedness against other alternatives also follow. In any inferential procedure, deriving a confidence interval is always desired. We now derive a confidence interval for a median using Wilcoxon sign rank test. The idea is to use the acceptance region of such a test. Now, the test statistic can be looked upon as a sum of m equal to n into n plus 1 by 2 positive Walsh averages. Then, due to symmetry, the acceptance region of the non-randomized level alpha test for testing theta equal to 0 against theta not equal to 0 can be expressed as C less than equal to T naught less than equal to m minus C, where C is such that the probability content exceeds 1 minus alpha under the null hypothesis. Now, from the theory of order statistics, it follows that for any k, x ordered r less than k if and only if at least r x observations are less than k. Then t theta less than equal to m minus c is equivalent to m minus t theta greater than equal to c. Now, m minus t theta is a number of Walsh averages less than theta. Then, m minus t theta greater than equal to c is equivalent to theta greater than w ordered c, where w ordered I for I from 1 to m are the ordered Walsh averages. In a similar way, we get that t theta greater than equal to c is equivalent to theta less than w ordered m minus c plus 1. Thus, we finally get c less than equal to t theta less than equal to m minus c is equivalent to w ordered c less than equal to theta less than equal to w ordered m minus c plus 1. Thus, we get c less than equal to t theta less than equal to m minus c is equivalent to w ordered c less than theta less than w m minus c plus 1. Hence, the probability that the random interval w ordered c, w ordered m minus c plus 1 covers theta is nothing but probability c less than equal to t theta less than equal to m minus c evaluated under theta. Since the distribution of t theta under theta is nothing but the distribution of t0 under theta equal to 0, we get probability c less than equal to t theta less than equal to m minus c under theta is equal to probability c less than equal to t naught less than equal to m minus c under h naught, and the probability c less than equal to t naught less than equal to m minus c exceeds 1 minus alpha, since we have used a size alpha or level alpha test. Hence, the random interval from w ordered c to w ordered m minus c plus 1 is a confidence interval for theta with confidence probability at least 1 minus alpha. Now, for a given dataset, the Walsh averages form a two-dimensional array, and we shall demonstrate the calculation and ordering of such averages. Suppose n equal to 4 and the observations are -2, 5, 8 and 13. Then we have m equal to 10 Walsh averages xi plus xj by 2. Now consider the two-way table with row and columns both indicated by x1, x2, x3 and x4. Since we need to maintain I less than equal to j, consider the lower portion of the diagonal element in each column. Look at the first column where the diagonal element is -2. The next element is the average of -2 and 5, that is 1.5, which is placed just below -2 and so on. Now think of a single column comprised of the elements of each column, that is a total of 10 values. This column then gives the Walsh average values. Sorting this column, we get the ordered Walsh averages, that is the ordered values of W. Now we shall see whether the asymptotic normality holds for T. First of all, note that under the null hypothesis, T equal to summation I from 1 to n Izi is the sum of independent but non-identical random variables. Then under the null hypothesis, the standardized variable t minus expected value of t whole thing divided by square root of variance of t is asymptotically normal provided Lyapunov's condition is satisfied. Now Lyapunov's condition will be satisfied if we can show that RL tends to 0 as n tends to infinity. Now the numerator of RL involves the sum of third order absolute raw moments of Izi, and the denominator involves the 3/2th power of the second order absolute raw moments of Izi. Since expected value of Zi square is nothing but expected value of Zi cube, which is half, it is straightforward to show that the above condition is satisfied. Hence, we have asymptotic normality of the standardized Wilcoxon sign rank statistic. Once we get asymptotic normality, large sample tests can be performed using this standardized value t star. For example, consider testing theta equal to 0 against theta greater than 0. Then the corresponding large sample test is non-randomized and rejects the null hypothesis if the observed value of t star exceeds tau alpha. Similarly, the large sample tests for the other hypothesis can also be constructed. Now, we shall describe an application of sign rank test. Actually, this test can be used to check the symmetry of the underlying population. Suppose xi, I from 1 to n are n IID observations from an unknown distribution capital F. Assume that capital F is a continuous distribution. To test the null hypothesis that F is symmetric about median theta naught, that is, under the null hypothesis, the distribution of xi minus theta naught and theta naught minus xi are the same for each I, then T can be used to test the symmetry. The critical regions are exactly the same as given before, but the interpretation of the final result is different. Suppose the null hypothesis is accepted, then it is concluded that F is symmetric about median theta naught. However, rejection of the null hypothesis is difficult to explain. Suppose the null hypothesis is rejected, then either F is symmetric with median not equal to theta naught, or F is asymmetric with median not equal to theta naught. However, such a broad conclusion in general lacks conclusiveness, and hence when this null hypothesis is rejected, the test is inconclusive. Now, we consider sign rank test for paired data. we have already indicated situations where we get paired data in the context of sign test. Suppose xi, yi, I from 1 to n are n pairs of observations from a unknown continuous bivariate distribution fxy. Then the null hypothesis is that xy and yx, that is the joint distribution of xy, is the same as the joint distribution of yx, that is the variables are exchangeable. Then suppose the median of the distribution of difference x minus y is indicated by theta d. Then under the null hypothesis, theta d equal to 0. Thus the objective is to test the null hypothesis theta d equal to 0 against the usual one-sided and two-sided alternatives. Naturally, theta d equal to theta dash indicates that x observations tend to be theta dash units larger than the corresponding y observations. Thus, statements about theta d give information about the relative locations of the marginal distributions. Then, the appropriate procedure is simply the Wilcoxon sign rank test based on the new sets of observations di, which is defined as xi minus yi for I from 1 to small n. Such procedures are referred to as paired sample sign rank test. We have already mentioned that sign rank test and sign test are both competitors of t-test. Then the question is natural, which test is best? Of course, the test with higher power is preferable. Now, we shall give a comparative picture of the power of two tests. Suppose 10 observations are taken from a normal distribution with mean theta and variance unity to test theta equal to 0 against theta greater than 0 at size 0.056. Then the power function of the sign rank test can be expressed. Now consider the corresponding sign test. Define pi as the probability of x1 greater than 0 under theta, which is nothing but phi of theta. Then the power function of the sign test can be obtained using the fact that the sign test statistic S has a binomial distribution with parameters 10 and pi. Now, calculating the cutoffs, the power function of the sign test can be plotted. But the distribution of sign rank statistic is not tractable even under the null hypothesis, and hence we use simulation to get the powers for different values of theta. From the figure, it is seen that the power curve for sign test is always below than that of the sign rank test. The reason is that unlike sign test, sign rank test incorporates symmetry of the underlying distribution through the test statistic. It also uses the relative position of the data in addition to sign. Thus, sign rank test gives more power. Thus, we conclude that if the underlying distribution is continuous and symmetric, sign rank test is the most appropriate option. It is always a good option when there is any doubt about the normality of the underlying symmetric population. Further, it is better than the test based on t-statistic for some non-normal distributions. We shall discuss this particular feature in future. We thus have discussed different properties of Wilcoxon sign rank test. However, Wilcoxon sign rank test is based on location model under symmetry. But there may be other underlying distributions, there may be some scale models, and there may be asymmetry as well. So in such cases, Wilcoxon sign rank test is not justified. In our next module, we shall discuss the so-called goodness of fit hypothesis. That is, whether the data arise from a particular population. And these are all known as goodness of fit problems. And in our next module, we shall discuss all these things in detail.